Thank you very much for the opportunity to speak. My apologies that I can't be there in person. The more I appreciate that I can give this talk remotely. So what I want to talk today about is about how we can unravel reionization with 21 centimeter galaxy synergies. And the question I have been asking myself essentially is like, first of all, like how did reionization proceed? And what was it ionization morphology? So put this short, essentially, what was the ionization history of the intergalactic medium? And which sources drove reionization? So do we have a scenario where the few bright galaxies drive reionization, you have a few large ionized regions? Or do you have a scenario where more the faint galaxies drive reionization and you have more smaller ionized regions that grow over time? And so in this aspect, I was wondering if you consider that the two observables that we will have or already have, the 21 centimeter signal and also high redshift galaxies, what can we learn from them? And specifically, I have been looking at like what happens if you cross-correlate these two data sets. And I believe Andre has already a bit talked about this, but I want to dive a little bit deeper. So the first question you can ask yourself is actually, how does the large-scale 21 centimeter galaxy cross-correlation power evolve across cosmic time? And so I'm pretty sure you have seen this before. So in the top panel, you have sort of an idea how the 21 centimeter signal special distribution evolves across time. And what you clearly can see, we have this characteristic shape that as the galaxies form, the 21 centimeter signal goes into absorption. When heating begins, it starts heating, and eventually it becomes into emission also during the epoch of reionization. And the key thing is, as you can see here, I'm showing you sort of the sign of the cross power spectrum. And theoretically, you would expect during cosmic dawn and reionization sort of to have 3 sign changes. And to walk just briefly through this, like when the first galaxies form, you have sort of in dense region, you have a stronger Lyman alpha coupling. So these regions will have a stronger absorption signal in 21 centimeters. So your cross power will be negative. Then as heating then continues, you start heating around the galaxies. So your 21 centimeter signal becomes weaker in absorption and stronger in emissions. So you see a positive cross power here. And there's actually also then the next sign change when you go from positive to negative cross power is essentially tracing the end of heating. And for anyone who is interested, I think there was a really nice paper by Morivaki et al. 2024. And she really looked at this in detail. What I want to focus now is essentially on the signal during the epoch of reionization and after heating. So essentially when the ionized regions start wiping out the 21 centimeter signal and we see a negative cross correlation. All right, so what can we learn from these 21 centimeter galaxy cross correlation and cross power spectrum during reionization? So I think the first thing we need to think about, which galaxy probes do we want to tackle here? And I think here it's important to keep in mind that not only you want to have sufficient spatial resolution, so you can resolve the galaxy spatially, but also in redshift space. And for this reason, because you want to also resolve them in redshift space, so along the spatial scale, along the line of sight, what we often go to are essentially line emitters, because for those you can determine the redshifts rather well. All right, so cross correlations, what would we expect? So what I'm focusing on now is a lot of 21 centimeter Lyman alpha emitter cross correlation functions. And here I show you sort of a slice of a simulation where in blue, you see the 21 centimeter signal. So the darker the blue, the stronger is your 21 centimeter signal in emission. And in the red stars are essentially Lyman alpha emitters, where larger stars essentially indicate a larger or higher Lyman alpha luminosity. What you expect now if you cross-correlate these two fields is that on small scales, so just around the Lyman alpha emitters, you don't expect any 21 centimeter signal. So on these scales, you expect it to be anti-correlated. However, now you can imagine if you go from a galaxies like further out at a larger radii, it becomes sort of random in the end, like whether you hit an ionized or a neutral region. And so that is the reason why at larger scales, the cross-correlation essentially becomes zero. It's not correlated anymore. Okay, so if you look at this shape and you look at different reionization simulations, you will find a lot of simulations have predicted very similar shapes. So if you look here at the results from Kubota 2017, Henniger 2020, Weinberger 2020, Ranbeck, they all use kind of different simulations and reionization schemes or radiative transfer. But they all roughly find a similar shape. So you have the anti-correlation on small scales and the non-correlation on larger scales. But if you look now in detail, then you will start finding differences. And particularly if you focus, for instance, like on the small scale power, we can see that there are different amplitudes, although they have like a similar neutral fraction. So here we have minus 0.4, versus here we have minus 0.3 at a similar neutral IgM fraction. And so the question I was asking myself, why is that the case? What drives exactly the shape of the 20 Lyman alpha emitter cross correlation? And to do this, I decided I want to do two different reionization scenarios. So going back to my original question, like, did more the bright or the faint galaxies drive reionization? And to do this, I used the Astreos framework. And for those who are not familiar with this, essentially what the Astreos framework is, it couples a dark matter only n-body simulation to a semianalytic galaxy evolution and a semi-numerical reionization scheme. So what we end up doing is essentially you take the density distribution and the dark matter merger trees from the n-body simulation. We post-process the merger trees with a semianalytic galaxy evolution model. And this includes essentially gas accretion, star formation, the most massive stars, explosive supernovae, and enrich the galaxy with metals and dust, and also emit sort of the ionizing photons. And we have also a prescription how many ionizing photons actually can escape into the intergalactic medium. And then on the fly, for each snapshot or time redshift, we essentially compute, if we have all these galaxies, how would the ionized regions grow? And because we track this on the fly, we actually can also account for radiative feedback from reionization. Okay, so this is a framework with which I did my two simulations with whether the faint or bright galaxies drive it. And so here you see the results. So the key thing about these simulations is they actually reproduce the Planck optical depth. They also reproduce the UV luminosity function at redshift 5 to 10, and also the Lyman alpha luminosity function at redshift 6.6 and upwards. So in the top row, you see the ionization fields for the scenario when the faint galaxies drive reionization. So as before, you see like the smaller ionized regions, and in blue, in red, you see the Lyman alpha emitters. And in the bottom panel, when the bright galaxies drive reionization, and you already can see your ionized regions are larger, they're actually also slightly more spherical and more clustered. All right, so the key question now is like, Lyman alpha emitters have a special sort of property. So because the Lyman alpha radiation is sensitive to neutral hydrogen, what happens is that they essentially need to lie in the most ionized regions. And so we just wanted to check whether in our Lyman alpha emitter model, they really lie in the ionized regions. And so what you see here on the left side, essentially the neutral fraction of the IgM versus the overdensity. And then you see in the colorful contours where the Lyman alpha emitters lie. And what you can conclude from here is essentially they lie in more or less very ionized regions. So this is essentially crucial if we want to understand the cross-correlation function. And so what this allows us to do is to formulate an analytic estimate for the cross-correlation function. And what essentially we find that during reionization and after heating, the small-scale amplitude scales as minus the neutral fraction of the IgM and the density in the neutral regions. And so this is actually really interesting because now you can compute for these different scenarios whether the average density in the neutral regions differ. And indeed it does. So if you compare the scenarios where the faint galaxies drive reionization, what you essentially can see that the ionization fields, they follow more closely the underlying gas density field. And that results in, if you look at the average overdensity of the neutral region as a function of the IgM neutral fraction, that we can see the average overdensity is lower. And so this means vice versa, if reionization is driven by bright galaxies, this average overdensity is slightly larger, particularly towards the end of reionization. And here it's also interesting to note, if you essentially were going to measure the 21 centimeter signal in a bunch of regions which don't host Lyman alpha emitters, what you will see, you essentially would detect on average a slightly larger 21 centimeter signal than in a scenario where the reionization would be driven by the faint galaxies. And I think the other thing which you really notice, which is shown here in the dashed lines, essentially they show like a far larger variance across these regions. And this is purely because you have more symmetric regions and they follow less the underlying filamentary structure. Okay, but now back to the cross-correlation amplitude. So if we now look at the cross-correlation which we have computed from the simulations, these are the results. So you have here on the left-hand side the scenario where faint galaxies drive reionization, and on the right-hand side where the bright galaxies drive reionization. And as we expect, as reionization progresses, the overall 21 centimeter signal drops. And so the cross-correlation amplitude on small scales starts dropping because your overall 21 centimeter signal is dropping. So the difference between this 21 centimeter signal around the Lyman alpha emitter and the global mean becomes smaller. The other thing I think you immediately can notice, if we compare like when the universe is roughly 50% ionized, and that happens in both scenarios around a redshift 7, you can see in the case where the bright galaxies drive reionization, actually the amplitude is larger than if the faint galaxies drive reionization. So this directly reflects this density in neutral regions, which is larger if bright galaxies drive reionization. So far, this was very predictive, but we actually wanted to go a step further and ask ourselves, can we actually describe the entire cross-correlation function analytically? And so if you think about this, essentially what the cross-correlation describes is sort of the average profile, 21 centimeter profile around a Lyman alpha emitter. And if that is the case, then actually you can use the size distribution of the ionized regions around the Lyman alpha emitter to formulate then via the cumulative distribution function of that size distribution, an analytic estimate for the cross-correlation function. And if you fit this now with the dotted line, for instance, with the log normal function, you actually find that a log normal distribution reproduces these kind of shapes rather well. All right, so this was the cross-correlation function. And of course, these characteristics or dependencies on the ionization morphologies, we also find in the cross-power spectra. So how do we find this? First of all, sort of the typical size of the ionized regions you can see in the sign change of the cross-power. So what you see here in solid lines is essentially negative. What is dotted here is positive. So you can see around these scales, you see a change in the sign. And so this sign change essentially traces a typical size of the ionized regions. So definitely you can see the typical size of the ionized regions are different in these two scenarios. But I also want to highlight here, if you look at the large scale power, you have a more large scale power in the case when the bright galaxies drive reionization. So when your average density in the neutral regions is higher. The question remains now, which of these features can we actually measure? And so what I did for a survey, which assumes sort of SKA1 low and some kind of Roman Grism survey with a redshift uncertainty of 0.02, a Lyman alpha depth, we detect everything down to 10 to 42.8 ergs per second, and maybe a rather optimistic field of view of 10 square degrees, then you see here in the shaded region essentially the observational uncertainties. And I think what you immediately can see that it will be hard to detect scales where we can see or trace a typical size of the ionized regions. And we will mostly rely on the large scale power. So, but in general, I think it's also worth asking, what type of 21 centimeter in galaxy surveys would we need to do this, and how does this scale? So I think Andre mentioned this already a little bit. I think I go a little bit into the detail in a different way. So in generally, when you think about the uncertainty of the cross power spectrum, it is given essentially by three contributions. So on the one hand, you have the sample variance from the 21 centimeter as well from the galaxies. And then from the 21 centimeter signal, you get also the thermal noise, which depends on your radio interferometer. And for the galaxies, you actually also have the shot noise. And so how do these determine, and on which scales do they determine your uncertainty of your cross power spectrum? So first of all, if you look at the shot noise from the galaxies, we can see it scales with the number density of the galaxies. So the higher the number densities of the galaxies, the lower is the shot noise. And similar, the lower the redshift uncertainty, also the lower is the shot noise. So the lower the shot noise is, the more you can actually detect, or the lower are your uncertainties towards larger K modes. I looked at this also to put this a little bit more into context. So what you can see here is, for instance, the cross power spectrum redshift 7, and in gray you see the observation uncertainties for our default parameters here. And so if you, for instance, change here the redshift uncertainty, you can see how your signal to noise ratio of the cross power spectrum redshift 7 changes. And you can clearly see if you decrease or increase your redshift uncertainty, then your signal to noise ratio goes down, and you also shift your sensitivity to larger scales. And similar, the same exercise you can do for the number density of galaxies. So this is basically encoded here in terms of the minimum Lyman alpha luminosity that we are going to detect. What this means here, essentially, if we have high Lyman alpha luminosities, we have less Lyman alpha emitters, and if you have low Lyman alpha luminosities, we have more Lyman alpha emitters. So therefore, as we go basically decrease our Lyman alpha luminosity, the more galaxies we will see, and also the higher will become our signal to noise, and the more slightly we can push also to smaller scales. And the next part, so this was mostly limiting sort of the small scales or large K modes. The thermal noise from the radio interferometer sort of increases with increasing K. And what you can do essentially to lower this, mostly I think it will end up in the intermediate K modes, you can increase the observing time or the number density of your antennas to push this down. And finally, the sample variance essentially dominates the uncertainties in your low K modes or your large scales. And this is what you can do by increasing essentially the survey area, so the field of view. And so if you show you here a similar plot, if you now plot again your signal to noise ratio as a function of the field of view, you see also very nicely as your field of view becomes larger, your signal to noise ratio becomes larger, and you also can push slightly to smaller scales. All right, so I think what was also, also pointed out, you already can see there is sort of a tension in terms of if you, from the 21 centimeter side, you would prefer to have large surveys to push down your observational uncertainties. While from the galaxy survey side, you actually would like to have like deep surveys to reduce your shot noise. But I think combining both will be really hard. So coming back to the question, like, okay, how can we distinguish our two models? In the past few days, I was wondering, okay, if I go through my survey parameters, so what I mean by here is the survey parameters is the redshift uncertainties, which you see here in the top, the minimum Lyman alpha luminosity, so the depth, and your field of view. And I was wondering, okay, for which survey parameters could we best distinguish between, in this case, our two scenarios? And so essentially what this is, you sort of compute a chi-squared, and I did it in this case just for summing it over the redshifts, the cross-power spectrum redshift 7, 8, and 9. This is just to have like a first idea, and it's very much in progress. But I think what you already see, if you assume a redshift uncertainty spectroscopy-like, GRISM-like, or narrowband-like, you see directly for narrowbands, we get very rather low sort of chi-squared values, which means that we cannot well distinguish between the two models. So the higher this value is, the better you can distinguish between the models. And you already see, like with GRISM, and you can do a much better job. And actually the difference between GRISM and spectroscopy seems to be not that large. I guess it's mostly because the constraining power comes essentially from the large scale modes. And this is also very interesting because what you also see here from the contour lines essentially is that it does not seem to depend very much on your survey depth. And this is, I think, another indication that most of the difference comes from the large scale power, I assume, because we cannot really track the sign change here in the cross power spectrum. And so this sounds maybe rather negative, or I think also what I could find from here that the most constraining power essentially, or differentiating power, comes from the lowest redshift, because at higher redshift, you don't have many Lyman alpha emitters. But I think one thing I want to also highlight is these simulations were tuned to the observation constraints we had pre-JWST. And so recently we have developed a new model where essentially we have changed the IMF and it becomes top heavier in galaxies that have higher specific star formation rates. And this has two implications. So on the first, you have far more galaxies with a top heavy IMF early on. So reionization starts earlier, but reaches the middle of reionization similarly and has very similar ends. So there's not much difference. But the key point is, like, early on, you already have ionized regions. And secondly, what also happens if you have a more top-heavy IMF, you have more ionizing photons output. And so you can also produce a higher intrinsic Lyman alpha luminosity. And so this brings me back to the right panel here. So what you see here is the Lyman alpha luminosity function. The dashed dotted shows you essentially the salpeter IMF, the solid line, the evolving IMF, which is top heavier at higher redshifts. And what you can take away from this, essentially, that above redshift 8, your number density in Lyman alpha emitters increases around the typical Lyman alpha luminosities you would target in observations, around by 0.6 dex.
And we are almost at the end of the time.
Yes. So what you see then also, if you go to higher redshift, this difference becomes more and more stronger. So I think this is just sort of the positive note, I think, where we need to check. And therefore, then I leave you with my summary. Thank you.
Thanks for the very nice talk. And then we have some questions from here. Prashun, please go ahead.
A nice talk. So I was just wondering, so you are going to K modes 1 megaparsec or even beyond. So is the redshift space distortion already included in your delta?
No, they're not included.
But it will have some effect probably in the cross correlation as well.
Possibly, yeah, I guess some, but I'm not entirely sure. I would need. I'm not sure. I would need to think about it a bit more.
Thanks.
Hi, Anne. Thanks for the very nice talk. The comparison that you did for the slit spectroscopy and the GRISM, you mentioned that they were comparable, but I noticed that your field of view axis is the same for both. And I think that's not really fair, because spectroscopy, we're not going to have 10-degree field of view spectroscopy because we need to follow it up. And it's a very expensive kind of thing. So like more than like 1 or 2 is going to be super, super hard. And if I interpret that correctly, it seems like it even strengthens your claim that we can really only do it with GRISM. Do you think that's fair?
Yeah, so I mean, this is essentially sort of the takeaway, I think, also from this. No, I totally agree with you. Spectroscopy, we can't on these large field of views. This was mostly to scan the parameter space and get an idea.
And in this case, did you have like an SKA type layout? Maybe I missed this with like, what was your foreground?
Yeah, so essentially we use the SKA stations, from SKA1 low. We only include baselines up to 10 kilometers. And otherwise, it's essentially all the uncertainties are computed by 21 centimeter sense, I think similar to what Summer has been doing.
Any other question? Okay, if not, let's thank the speaker.